Hi folks, this is Physics Module 15. So today we're going to talk about circuits and direct current. So direct current is something that you would experience when you're using a battery, where charge is just going from one terminal to the other. This is not like alternating current, where if you plug something into the wall, you have an alternating current. That's for another day. So we're talking about batteries and direct current today. So a battery has a potential difference, which we've also called many other things like electric potential or voltage. They all mean the same: potential difference, electric potential, and voltage, right? And so the battery's potential difference is equal to its voltage from one terminal to the other. You need to watch the sign of the voltage, and the sign will just match whichever terminal you actually end up at. So if an electron is going from the negative to the positive terminal, then the change in voltage will be positive. You ended up at the positive terminal. So when you have a battery with a loop of conductive material from one terminal to the other, then that allows current to flow, a closed circuit, right? Current depends on the voltage and the resistance in the circuit, and that's Ohm's law, V equals IR. So voltage is like water pressure, as an analogy. It's a faulty analogy, but it'll help you kind of conceptualize the idea. So voltage, think of it as like water pressure, right? Like how much energy is there in each charge that's moving through, like how much energy does each electron in the circuit have? And that's how you measure your voltage. And so if you think of water pressure, right, like if the shower is raining down on you, like how hard is the water coming out? Is it enough to get the conditioner out of your hair, or is it just like that sad trickle in some showers where it won't actually rinse your hair out? So water pressure, that force kind of is sort of in the analogy like voltage, energy per charge. So that unit, volt, is really a joule over a coulomb. Right, so the energy or joule over the charge in coulombs. So current is another one of the things that we're talking about today. So current is defined as kind of the water flow or rate. It's something more like velocity. If we're looking at our water analogy, it would be like gallons per second coming out of your shower, right? Some showers can have a lower water pressure, like voltage, but lots and lots of water gushing out. And some can have a high voltage or high water pressure, but not that much water actually in gallons per second coming out. So current is like gallons per second. So we think of it as a flow of charge per second. So the unit for current is amps, or amperes, and we measure that in coulombs per second. Resistance is the other thing in Ohm's law. Resistance is like something that prevents the flow of charge. And it's something like friction. Essentially, the resistance in a circuit converts energy to something like heat or light, just like mechanical friction converts this mechanical energy into heat. My hands heat up when I do that. So when you have something with a large resistance, then you may, if it's a toaster, you'll be producing a lot of heat. If it's a light bulb, you'll be producing light, etc. And so let's take a look at Ohm's law. Okay, so on the board now we can see Ohm's law, V equals IR. V for voltage, I for current, which is measured in amperes, so that I doesn't really help us out there because the unit is amps. And then R, which is resistance, and it's measured in ohms, which is the omega here. And so we'll do one little quick problem just to make sure we're familiar with Ohm's law. So I have a 6-volt battery, and it has a 2 ohm bulb, which is the resistor. What will the current be in that circuit? So Ohm's law is super easy. Just plug in So voltage is 6 volts. And then resistance is 2 ohms, and I want to find current, which is I. Right, so obviously I divide through by the 2, and I find current to be 3, because 6 divided by 2, and then the unit for I is actually amp, so 3 amps. So my current would be 3 amps if I have a 6-volt battery and a 2 ohm resistor. So I'll put another problem on the board and show you how to draw some simple circuits. Okay, so we have a circuit drawn here on the board. The battery is shown by these lines, and resistors are shown by these little jagged lines. So we've got a 12-volt battery, and then we have a 2 ohm resistor and a 4 ohm resistor. And because as our current flows around this battery, you can see that it would have to flow through both resistors. There's no choice but to go through one and then through the other and back around. So when we have a circuit like this, we call this a series circuit, meaning that both resistors are in series. The current has to flow through one and then through the other. If one resistor fails in a circuit like this, then you end up with no electricity being able to flow because there's a break in the circuit, and it would be like an open circuit. When you have 2 resistors in series like this, you simply add them up. And their total resistance is just equal to the sum of their 2 resistances. And so we just add 2 and 4, and we find that our resistance in the circuit is just 6 ohms. So V equals IR again. Our battery is 12 volts. And then we'll divide by our resistance, which is 6 ohms, to find our current. So current is 12 divided by 6, which is 2 amps. Again, I think, was that the answer to the last one too? I don't know. Oh no, the last one was 3 amps. Okay, so we have a 2 amp current in this particular circuit. In a series circuit like this, you can see charge has to flow through each resistor. But current isn't, the water pipe analogy kind of breaks down because current isn't like a hose that comes empty and has to be filled with water before anything can flow at the end, right? Electrons are already present in the material of the circuit, right? If we have a copper wire connecting 2 ends of a battery, the electrons are already present in the wire. They don't have to come from the battery and fill the wire up. And so the electrons can move fast, but only part of their direction is actually from one terminal of the battery to the other, right? Maybe they're supposed to be going this way, but maybe they're kind of wandering around. And so electrons aren't moving like close to the speed of light like you kind of think of electrons doing when they're inside a circuit. Let me put another circuit on the board here. Okay, so one key point to know that I'm not positive is like necessarily covered in your book, maybe some of this isn't, but things that are important to know about current. So current in a series circuit is constant. Current is going to be constant throughout the whole thing. So if you solve for current, then you can use that and plug back into other equations to find out other things for a series circuit. So in this case, with the black circuit here, I have a 6-volt battery and a 2 ohm resistor and a 4 ohm resistor. So can you calculate and find the current in that circuit? So hit pause, find the current. Okay, so the current in this circuit is 6 volts divided by 6 ohms, which is 1 amp, right? Okay, so we know that everywhere in the circuit has 1 amp. And in fact, something we didn't talk about, which of the 2 light bulbs would light up first when you connect the circuit and current starts to flow? So take a guess at that for a minute. And hopefully, if you think about that, you said neither, because as soon as the circuit is hooked up, the electric field travels at the speed of light, and both bulbs should light at the same moment. just because the electric field causes every electron in the circuit to start to move at the exact same moment. And so both bulbs should light at the same time. But back to this problem. So we have 1 amp of current everywhere. Now both bulbs will experience a different voltage drop. I don't think your book goes into this, but if we could do the lab, which I'm starting to lose hope that we'll get to do together, but when we do the lab, hopefully you could see. So when you realize that you're always going to have 1 amp of current everywhere because current is constant in a series circuit, then you can say, well, 2 ohms times 1 amp means that I have a 2 volt voltage drop across this bulb, and a 4 volt voltage drop across this bulb. So the two resistors are different. They experience a different voltage drop, but they have the same constant current everywhere in the circuit, which is 1 amp. So if we look at this blue circuit, I have 3 resistors in the circuit. I have a 6-volt battery. So if we assume that the 3 resistors are identical, they have the same resistance. If all 3 resistors are identical, what is the voltage drop across one bulb? So hit pause and see if you can figure out the voltage drop across one bulb. I'm not telling you what the resistance is. I'm just telling you can divide up the voltage evenly, basically. So try to think that through. And hopefully you said that the voltage drop will be 2 volts across each resistor. So if I tested the voltage across 1, I should find the voltage drop to be 2 volts. If I put my voltmeter across 2, I should find the voltage drop to be 4 volts. And across all 3 should be 6 volts, just like the battery. So here's a question for you to think about while I change my board. Will the battery last longer with fewer or with more bulbs? Right? So if, for example, I just changed this and I made every resistor on the board a 2 ohm resistor. Let's say every resistor is now a 2 ohm resistor. So I've got a 6-volt battery with 2 2-ohm resistors and a 6-volt battery with 3 2-ohm resistors. Which battery would last longer? Would it be the one with fewer bulbs or the one with more bulbs? So hit pause and I'll change my board and then we'll come back and discuss that one. Okay, so if we look at that problem, I redrew these 2 circuits. So I have 3 2-ohm resistors in series here and 2 2-ohm resistors in series here. So we can calculate the current for both of those circuits. So if I have 3 2-ohm resistors, my current would be the 6-volt battery divided by the resistors added up, which is 6 ohms. So I find my current to be 1 amp in this black circuit. Over here, with just 2 resistors instead of 3, then my voltage is still 6 volts because I have the same battery, but my resistance is only 4 ohms because I only have 2 resistors, and so my current is 1.5 amps. So when you have a lower current with the same battery, you'll have a longer battery life. So actually the 3 bulbs which cause the battery to have force out a lower current would actually extend the battery life, which is super counterintuitive and funny. So hopefully you can see I'm not going to use this green marker anymore, but we'll look at a different way to build a circuit, which is when you put resistors in parallel. So when you put resistors in parallel, the electrons have to choose a path. There's more than one way for them to go from one terminal of the battery to the other. So in this case, you can see I'm using a 6-volt battery. I have 2 2-ohm resistors, but they're not lined up like they are here, right? So when the electrons flow, they can choose this resistor or they can choose this resistor. They always go one way or the other. They don't go through both resistors. Each electron will go through one or the other. And so when we want to calculate the resistance of two resistors in parallel, then we use this formula, which people always forget at the end to kind of flip it. So you really want to pay attention. 1 over R equals 1 over resistor 1 plus 1 over resistor 2. And if you have resistor 3 and resistor 4, you just keep adding the reciprocal of those. And so if we plug that in, 1 over resistance equals 1 over 2 ohms plus 1 over 2 ohms. And you guys know 1/2 plus 1/2 is 1. And so we find 1 over 1 ohm to be 1 over resistance, which means that resistance is 1 ohm. Here. So when I have these two resistors in parallel, the resistance is 1 ohm. When I had those two resistors in series, the resistance was 1.5. Oh wait, that's current. We just add them up here. So resistance is 4 ohms. So you can see that in parallel, two resistors have actually less resistance than they did, than either one of them actually has by itself. Whereas in series, you just add them up, so they increase the resistance of the circuit. Adding resistors in parallel actually decreases the resistance of the circuit, which is another counterintuitive thing about circuits. So we could calculate the current for this. Now that we have resistance is 1 ohm with our two ohm resistors, you can calculate using Ohm's law. Again, here, I'll just see if I can fit it. V equals IR, right? So we have 6 volts divided by our 1 ohm resistance. And so 6 divided by 1 is 6 amps. So we have 6 amps of current. So when you put those two resistors in parallel, you've decreased resistance, so you've increased current greatly. So we have 6 amps of current in the parallel circuit, whereas we only had 1.5 amps of current when those same resistors were in series. When you have a series circuit, again, if one resistor gets burned out, then the whole circuit stops working because there's no way for electrons to flow from one terminal of the battery to the other. Whereas if we have a resistor burnout, if either of them burned out in the parallel circuit, then all the electrons would simply choose the path that still connected the two terminals of the battery. And so the broken one, of course, wouldn't work, but any other resistors in parallel would still be able to work, whether that's producing heat or light or whatever. I'll frequently talk about resistors in terms of little light bulbs. So this one would still light up, whereas this one would not because there's no pathway for the electrons to flow from one terminal to the other. This one still has a pathway. So obviously, old Christmas lights where if one burns out, they all stop working would be in, and hopefully you said series. And newer Christmas lights where if one burns out, the whole string continues to work are wired in parallel. All right, I need to change my board again. Okay, so now I want you to look at this problem and then hit pause and try your best, and then we'll come back and talk about it. So draw a circuit with 3 resistors that are in parallel, a 2 ohm, another 2 ohm, and then a 3 ohm in parallel, and then find the total resistance for that circuit. And hit pause, and then we'll come back with an answer. Oh, I should tell you there's a 6-volt battery. Okay, so hopefully you drew in your 6-volt battery and then you made them in parallel so that electrons can choose to go through either this 2 ohm or that 2 ohm or that 3 ohm resistor. And there are 3 separate pathways from one terminal to the other. Okay, so to solve for the overall resistance of the circuit, you use your formula 1 over R equals 1 over each resistor. And so I had to get a common denominator for 2 and 3, which is 6, of course. So 1/2 is really 3/6, and 1/3 is really 2/6. And then I just said 1 over R is 3 and 3 and 2, which is 8 over 6 ohms So then I found R to be 3/4 of an ohm. So what that means is I took a 2 ohm, another 2 ohm, and a 3 ohm resistor. If I put those in series, right, I would add them up and they would be 2 plus 2 plus 3, which is 7 ohms of total resistance if they were in series. But when I put those same resistors in parallel, that resistance is only 3/4 of an ohm. And so this also tells us why bulbs that are placed in parallel are brighter, right? Because when voltage is the same, like if I use the same battery and keep that constant, and resistance goes down, then obviously, according to Ohm's law, V equals IR, current has to go up, and that makes the bulbs brighter. So putting the exact same bulbs in parallel causes them to be brighter than when those same bulbs are in series because resistance is lower, meaning current will be higher. So let's see, what do I want you to do now? So now that we've calculated the overall resistance for this circuit, come back after you've calculated the total current for the circuit. So go ahead and find I for this circuit now that you have R and V.